We planned this telescope to see the absolute first worlds that turned on in the universe, and when we saw what it did, I'm actually attempting to comprehend, on the off chance that we have cosmic systems in the dark ages, how about we get back to, they shouldn't be there. So what needs to give? Are the data there? Is there a big issue with the information? On account of what the James Webb Space Telescope has seen, we now know that the universe isn't so old as we naturally thought. The next thing we learn will cause us to feel moronic if we assume we are that shrewd. The pictures coming from the brilliant telescope that people assembled are staggering. These enormous telescopes let us see back in time, despite the fact that it's only been 320 million years since the Big Bang. Now it takes a large number of years to make a universe like the Milky Way to see it for yourself. There's no doubt now, the JWST has given researchers more inquiries than replies to track down those responses. They've concocted a lot of ideas. Some individuals think there are dark stars, and others think the universe is significantly older than we suspect. Accompany us as we check out old worlds that don't check out and the latest thoughts that scientists have come up with. Will these thoughts turn out to be valid? How about we figure out everything? It all started in July 2022 with the Deep Field image. At the time, the JWST sent back its most profound infrared pictures, which showed an astonishing perspective on the distant universe. It also sent back the sharpest and most profound infrared picture ever seen. Webb's most memorable deep field shows the galaxy cluster SMACS 0723, which is loaded with a huge number of worlds, some of which are the smallest infrared objects ever seen. This deep field picture is a complicated mix of images taken at different wavelengths over the course of 12.5 hours of exposure. Because it is so heavy, SMACS 0723 functions as a gravitational lens, making some of the farther away galaxies look bigger. The galaxy cluster has a solid gravitational field that can bend light rays from galaxies farther away behind it, like how a magnifying glass can curve and bend images. A gander at SMACS 0723 from 4.6 billion years ago is displayed in the picture, which shows numerous galaxies in front of and behind the cluster. These worlds radiated light billions of years ago, which allows us to see some of the most recent worlds that were formed less than a billion years after the Big Bang. As the universe expanded, their light got increasingly long until it came to infrared wavelengths. Scientists have learned a lot about the majority ages, narratives, and cosmetics of these universes from this new information. This technology offers back a lot of data about every galaxy. The numbers show that light didn't hit Webb's mirrors for 13.1 billion years. This implies that this deep field picture assisted researchers in discovering some of the oldest worlds ever. We found an unusual old world called Maisie's Galaxy, which was named after the finder's young daughter. This galaxy is a deep look into the absolute starting point of the universe. Maisie's Galaxy is a major forward-moving step in the investigation of the universe. Despite it just appearing to be a dazzling orange spot, this genuinely average spot overhead is really one of the most ancient things in the universe. Researchers have now found out without a doubt how old the universe is at where Maisie's Galaxy shows up. Their results show that this infinite being formed when the universe was only 390 million years old. In terms of the universe, this is extremely young. It is one of the 4 oldest galaxies that people have ever seen. It was named for Stephen Finkelstein's daughter, who is 9 years old. He discussed how significant it was that Maisie's Galaxy was found. It lives in a time in the past of the universe that is so far away that we were unable to see it until the JWST came along. Finkelstein said this was the great neglected region where science still didn't have a clue what galaxies looked like or how they formed previously. Before the JWST was sent off, this was the situation. The data from the telescope showed that Maisie's Galaxy is one of the older ones, based on how significant it is. This astonishing galaxy was given a unique name that distinguishes it from the JWST's other discoveries in space, which typically have more formal names like C1019, C2782, and CRS.IT places youthful Maisie in the equivalent bunch as popular researchers like Fritz Zwicky, Edward Jamari, Stefan, and Carl Keenan Code, who all had worlds named after them. Maisie, then again, is unique since she acquired this honor at the age of 9. Stephen Finlan viewed this as a system in JWST information on the 9th birthday celebration of his girl. He kidded that it was called Maisie's system since he had continuously maintained that a system should be named after her. When the time had come to share the results, the name stuck, and the universe was known as Maisie's universe from that point on. Maisie is excited to have her name connected to such a significant cosmic system in the universe. Yet how do researchers figure out how old a star is? It's harder to sort out how old universes were in the early universe than it is to demonstrate a birthday. It utilizes a number called redshift to sort out the distance away a universe is and how long its light has been venturing out to contact us, and therefore what astronomical period we are in when we see it. Light rushes of various lengths are called groups. For example, blue light has short frequencies and high frequencies, while red light has long frequencies and low frequencies. When light comes to us from a distant source, like an early star, that source creates some distance from us as the universe extends. There is less energy in the light from the source, so the groups get longer and change frequency. To put it all more simply, blue light, with a high frequency and short wavelength, changes over time into red light, with a low frequency and long wavelength. The name redshift comes from the way that this change pushes light toward the red part of the electromagnetic spectrum. It sometimes even gets to the degree of infrared light, which individuals can't see. There is more redshift of light when it has been traveling through space for a longer time. Light from early systems, like Maisie's, has traveled for around 10 billion years before it gets to the JWST. The light that left Maisie's system was in the visible part of the electromagnetic spectrum. When it gets to the space camera, it has moved down to the infrared part. This is the reason the JWST is a particularly powerful method to study things that were around in the early universe. Long wavelength infrared light is exceptionally easy for this space camera to capture. As a matter of fact, it would have been extremely difficult to discover worlds like Maisie's before the JWST. Despite the fact that the Hubble Space Telescope was extraordinary, it wasn't sufficiently large or capable of covering enough redshifts to see systems that were so distant and had such a high redshift. From the beginning, researchers believed Maisie's universe was around 11.8 billion years old, in light of how brilliant the photos were. Using a couple of wide frequency channels to get a more exact age, they looked at the spectral lines made by chemical elements at certain frequencies. With the JWST's near-infrared spectrograph, it was calculated that Maisie's cosmic system had a redshift of 11.4. It's not as old as we initially thought, it's many years, in fact, younger. Still, it's exceptionally old. The JWST snapped the photo just 390 million years after the Big Bang. Maisie's universe is unique and not by any stretch like cosmic systems we see today. It would be unique in relation to universes like the Milky Way since it is a lot smaller. Things were denser back then, so universes were closer together and merged more frequently. Additionally, all the stars were exceptionally youthful because the universe was only 400 million years old. This made systems more brilliant and bluer than they are now. Right now, we're seeing it. Maisie's universe stands out because it's bustling, caught up with making new blue stars. This stage is known as starburst by stargazers. Despite the fact that Maisie's cosmic system is brightly redshifted, it is actually bluer than I suspected it would be because its stars are youthful, brilliant, and blue. There are a lot of stars in a blue ball shape. This also shows that Maisie's cosmic system has fewer heavy elements, with hydrogen and helium making up the greater part of it. Surprisingly, it is more brilliant than people figured early cosmic systems would be. This is a pattern the JWST has seen with other early universes. It suggests that stars might have formed more rapidly and efficiently in early systems than was previously suspected. This would have made the stars shine brighter and be easier to see. Finlan wants to utilize the JWST's mid-infrared gadget to dive deeper into Maisie's system. This will show more about its heavy element makeup and whether it has astronomical dust grains. In seeing that it's easy, Maisie's cosmic system is an early universe. Since it's brilliant, it's easy to study and measure things about it, like its mass, shape, and heavy element content. One of many systems helps us sort out what occurred in the start of the universe. Maisie's cosmic system used to be one of the most seasoned cosmic systems in the world, But that didn't last long. It's difficult to express an adequate number of beneficial things about the JWST. In November 2022, only a couple of months later, NASA found even more very old worlds. Most old cosmic systems of all time, researchers say, are being revealed by the JWST, showing us an entirely new world that conflicts with what we thought it would be like. In a part of ways, these early systems are totally different from one another. In the astrophysical journal Letters, 2 research papers were published, driven by Marco Castellano of the National Institute for Astrophysics in Rome, Italy, and Rohan Naidu of the Harvard-Smithsonian Center for Astrophysics and MIT in Cambridge, Massachusetts. These first outcomes come from Webb's larger study project, which includes the GLASS and SE early release science programs. Analysts took a gander at the GLASS JWST pictures for just 4 days and found 2 exceptionally brilliant worlds. These cosmic systems were formed somewhere between 350 and 450 million years after the Big Bang, and each has a redshift of around 10.5 and 12.5. Only a couple of days after Webb shared its first data, researchers were stunned to find starlight from the farthest spans of the universe. Researchers discovered a system called GLASS Z12 that is very far away. It is believed to have started 350 million years after the Big Bang. Universe GIN Z11 held the previous record. It was 4 million years after the Big Bang and had a redshift of 11.1. The Deep Sky Projects at Hubble and Keck Observatory, established in 2016, provided these observations. These findings are staggering and show that space science is entering an entirely new age. One of the individuals who composed the study says that these outcomes resemble finding a lost city during a verifiable dig. The very brilliant light from these early sources makes it difficult for us to grasp how universes form. We might have been off base about how the universe began. Perceptions like these have led cosmologists to agree that numerous cosmic systems in the early universe were much more brilliant than previously thought. This new data makes it possible for Webb to track down additional early cosmic systems in ongoing sweeps of the extremely far sky. Space experts were exceptionally intrigued by these outcomes because it is easier to see bright systems than feeble ones. The time span of our reality has now been raised in doubt. It seems as though these worlds began to structure just a brief time after the Big Bang. Along these lines, peculiarity, they had the option to continue to gain mass, which caused them to become exceptionally huge over the course of their lives. There are some abnormal things about these stars. The temperature of their surfaces is about equivalent to the Sun's, yet their brilliance is a billion times more noteworthy, as splendid as a world loaded with stars driven by combination. Perfectly makes sense of another secret that researchers are struggling with sorting out. When these immense dark stars reached the finish of their lives, they would have collapsed into enormous black holes. This could likewise make sense of the presence of some exceptionally old supernova remnants. Huge explosion, which is a great deal sooner than anybody thought. The dim ages, the time in the early universe, might have completed a parcel prior. If this is valid as an illustration of how old that is, these cosmic systems probably formed when the universe was just 1% as old as it very well might be now. That is an exceptionally brief time frame when you think about how old the universe is currently, 13.8 billion years. One of the other colleagues said that estimating the types of these early universes was astounding because it went against the vast majority's thoughts on how the principal universes formed in the early turbulent universe. This is on the grounds that the shapes were quiet and ordered, not flung around or wrecked. This finding was made conceivable by Webb's clearer infrared pictures. Cosmologists saw that these systems are not the same as the Smooth Way and other huge cosmic systems we see today, very much as they did with Maisie's universe. But there's another riddle. Researchers don't know why the 2 universes that these groups tracked down emit such a lot of light. They are contemplating 2 choices. They could be extremely huge and have many low-mass stars like later cosmic systems, or they could be significantly less enormous and have less but extremely brilliant stars called population 3 stars. These stars would be the first stars in the universe. They would consume at exceptionally high temperatures from unadulterated hydrogen and helium, making heavier components before stars use atomic combination to create heavier components later on. We can't track down these types of brilliant early-stage stars anyplace in the nearby universe. This means them any longer, and the light we see from them is billions of years old, which makes them extraordinary. The source that is the farthest away looks extremely minimized, and the tones show that it has a population of stars that are for the most part liberated from heavy components. It might even have population 3 stars in it. However, network groups are the specific ones that can offer us strong responses. The infrared shades of these two universes are utilized to measure how far apart they are. Later on, more spectroscopy estimations will show how light curves as the universe extends. These estimations will be affirmed by various measures made in space. While we sit tight for these readings, the JWST has found significantly more intriguing things, like dark stars. There are something else astonishing things that the JWST sees as each day than just old systems. Researchers are stunned by the odd things they're finding with this device. In August 2023, one of these discoveries occurred. Researchers think they tracked down something called dark stars. During this time, researchers don't actually know for certain if dark stars exist. The thought was first put forward in 2007. Rather than normal stars, dark stars get their power from dark matter annihilating itself. Dark matter is an undetectable substance that makes up 85% of the matter in the universe. Despite the fact that more exploration should be done on these conceivable dark stars, they could significantly alter the manner in which we ponder how stars structure in the early universe. Even though they are called dark stars, they are not the very opposite of the huge plasma balls we know. It is intriguing to feel that dark stars could have radiated 1 billion times more light than the Sun and been multiple times heavier, even despite the fact that they have never been seen without a doubt. Computer models show that they could have formed soon after the Big Bang from billows of unadulterated hydrogen and helium falling within protocosmic systems that were brimming with dark matter. Scientists wrote in the Proceedings of the National Academy of Sciences USA that no less than 3 distant objects that JWST had erroneously called universes could really be single giant dark stars. This overview, which was completed by the JWST and is otherwise called JADES, looked at these systems. GSZ-13, GSZ-12, and GSZ-111 were the things being referred to. If the viewing is demonstrated as true, it will be a significant finding. The review's co-creator says that right now it can't be demonstrated for sure that these things are dark stars. In any case, they have characteristics that are like both dark stars and systems that host combination-powered stars. With more perception time being the main thing, JWST technology could possibly clear up this uncertainty. Another co-creator believes that one of these dark stars will be found during the JWST's useful life. There are 2 potential ways that the universe's first stars came to be. Many people imagine that these early stars got their power from atomic combination, very much like stars do today. Yet, other than helium, they would have had practically no heavy components since those components hadn't formed at this point in the early universe. These are the same stars from population 3 that we talked about previously. However, there is an alternate, seriously fascinating thought. In 2008, researcher Free and her collaborators concocted an interesting theory. They felt that dark matter could have given the universe's first stars their power. The piece of this puzzling substance, which only reacts through gravity, is still for the most part a mystery in the early universe. Dark stars could have come from helium and hydrogen mists that were falling after the Big Bang. Numerous thoughts say that dark matter particles are unique since they are also their own antiparticles. All antiparticles have the same mass, but their electric or magnetic characteristics are opposite to those of the molecule they depend on. Take the positron as an illustration of something contrary to an electron. It weighs the same as an electron, but has a charge that is the opposite of that of an electron. When these two meet up, they annihilate one another. Assuming dark matter particles are their own antiparticles, then when they hit each other, they will annihilate themselves. It would also cause particles to separate when they hit one another in these falling mists. It might have set off a chain of molecule interactions that led to the formation of photons, electron-positron pairs, and neutrinos. Neutrinos would have left the cloud since they don't interact with matter. Particularly, most of these particles would have remained inside the cloud. The other particles would have given the hydrogen and helium their energy, which would have warmed the cloud and assisted stars with forming. Moreover, these stars would have looked like they were in little coronas. These are early protosystems that formed around 200 million years after the Big Bang, before heavier components than hydrogen and helium showed up. The most compelling thing that made up these smaller-than-expected radiances was dark matter, which made it ideal for these dark stars to form. This thick gathering of dark matter, as it were, existed in the early universe, which implies that dark stars could form during this time. Dissimilar to their atomic-powered peers, these stars remained pretty cool and didn't radiate the high-energy photons that stars as a rule do. Enormous dark openings have been found in the universe. These dark openings look too huge to even consider having framed rapidly from populous 3 stars that were fueled by combination. The analysts glanced through the JWST assortment of items from before the universe was framed around 14 billion years ago to track down these dull stars, as there wasn't much data about these articles. Electromagnetic outflows only indicated that 9 were remembered to be good candidates. The highlights of 3 of these were actually similar to those of dim stars. They had a high redshift, which implies they were old and came from a distant place. They also appeared to come from a single source, like a star rather than a galaxy. At this point, the scientists have only made a couple of observations of these objects, which means they can't conduct a more in-depth study at this time. A certain indication of a dull star's appearance would be a unique piece of the electromagnetic spectrum where light is absorbed by a helium isotope that is only seen in dim stars and not in galaxies. To find this sign, long-term observations are required, which is problematic since the JWST is already being used for other astronomy studies. Early outcomes, however, show that if these things were truly dim stars, 2 of them would be multiple times heavier than the Sun, and the third would be multiple times heavier. The study group is currently working on an automated method for finding more possible dim stars. Some of these may only need a short amount of time to be confirmed through observation. They hope to find many more potential candidates. If they could see a dim star directly, it would be an immense achievement. There are, however, alternative ways to track down dim stars, like searching for their fingerprints in the cosmic microwave background, CMB. The CMB is a weak radiation shine that is left over from when the universe was extremely hot and youthful. Noticing a dim star wouldn't just provide us with new information about how the universe came to be, but it would also give us an interesting opportunity to study how dark matter particles interact with one another. Observing these types of events would help us glean significant insights about how dark matter functions as a particle. Some researchers say that we were wrong about how old the universe is. Despite the fact that the dim star doesn't change much of what we already know, the age of the universe may not be as old as we think. We weren't joking when we said that the JWST is changing how we ponder the universe. We're discovering things that conflict with our existing knowledge. The JWST found galaxies that are extremely old, only 325 million years after the Big Bang, but these discoveries have led cosmologists to propose an intense hypothesis. Some researchers believe the universe may be twice as old as we thought. Most scientists agree that the Big Bang occurred 13.8 billion years ago, but Professor Rendragupta wants to change this to suggest it may be 26.7 billion years old. Another cosmologist utilized the Sean standard, which states that claims that are out of the ordinary need evidence that is also out of the ordinary. So, does Gupta have sufficient evidence to back up what he said? Before we can grasp his hypothesis, we need to understand how the cosmologist arrived at these numbers. It's difficult to determine how old celestial objects are, let alone the entire universe. This process relies on examining the cosmic microwave background, CMB, radiation and taking readings of how quickly the universe is expanding. The CMB only returns 300,000 years after the universe began. It's spread out into space and is the oldest radiation we can observe. Cosmologists determine the age of the universe by carefully analyzing changes in temperature in the CMB. Edwin Hubble, a researcher, proposed Hubble's law in the 1920s, which contributes to this understanding. It identifies the relationship between the velocities and distances of galaxies and helps to determine how quickly the universe is expanding. The Hubble constant is the name for this number. We can estimate how long the Big Bang lasted by tracing this development backward. On the other hand, Gupta's model takes a very different approach, relying on the concept of tired light. Fritz Zwicky first proposed this idea in 1929, which helps Gupta explain why photons from distant galaxies are redshifted. We now know that redshift occurs because the universe is expanding, which causes photons to stretch and lose energy as they travel. According to the drained light hypothesis, although this conflicts with what we currently understand, Gupta suggests that the redshift effect could be seen as a hybrid impact that isn't solely caused by expansion. If this hypothesis were allowed to coexist with the expanding universe, there would still be galaxies in the initial million years of the universe, but this is often referred to as the incomprehensible early universe problem. Researchers do not know why these extremely old galaxies formed so early. Physics and observations make it challenging to assess how old the universe is based on what we know now. Galaxies need time to evolve over the long term, developing stars and structures in various ways. However, powerful telescopes like the JWST have revealed mature galaxies that formed when the universe was very young, prompting questions about how galaxies structure and change over cosmic time. To address this incredible galaxy issue, Gupta proposes that the universe may be significantly older than we currently believe. He adds new factors that change over time, implying that galaxies formed long ago rather than just a few billion years back. These facts lead him to believe that the universe might be nearly 28 billion years old. Researchers generally do not agree with this hypothesis. They suggest that a more straightforward explanation could be that we do not fully understand how galaxies formed in the universe's infancy. There are even individuals who think the so-called incomprehensible galaxy problem is overstated. Researchers imagine that JWST observations raise certain questions about how galaxies formed in the early universe, but nothing is inherently impossible. Cosmology will not be dramatically altered by Gupta's ideas in the near future, according to specialists. Our current understanding of the Big Bang and the evolution of the universe relies heavily on observational data that has helped us explain numerous cosmological events. For Gupta's study to gain traction, it would likely require more research and theoretical development. According to the standard model of physics, the Big Bang occurred around 13.8 billion years ago. It has utilized data from numerous sources, including cosmic explosion data, observations of the universe's expansion, and the distribution of galaxies. Researchers do not believe Gupta's study is complete because it mainly examines cosmic explosion data. We need rigorous tests in various ways. However, Gupta's idea has garnered a lot of media attention, while some researchers dismiss it as mere hype, questioning the scientific validity of the study itself. Any theory attempting to explain the Big Bang must account for fundamental facts about the universe. It makes little sense to settle another mystery if it cannot explain existing data. What do you think? If more research is done, might Gupta be validated, or is this just another hypothesis that will lose support over time? Post your response below and click like to see more.